So, in our third speaker today in this session, camera technology, I'd like to welcome Stan Geertz from Prodrive Technologies, and the topic of his talk is challenges in advanced camera applications.
Thank you. So welcome everybody. So I'm Stan Geertz. I'm a systems architect, so I'm not a sales guy. In contrast to most of the other presentations, I'm not going to show actually our off-the-shelf products, which we have. So please visit our booth to have a look at those. But I'm going to show you some of the insights actually of the cameras and of our processes at Prodrive. So maybe I start with a question for the audience first. So I don't know who's familiar with Prodrive actually. I see one, but that's my colleague. So Prodrive is relatively new to this show. We were actually here 4 years ago as well. But we're not a young company. So we are founded in 1993. So we are there for 29 years already. And we have roughly 3,000 people working at Prodrive worldwide. So I think it's worthwhile to visit us as well. Oh, I should. Oh, yeah. Okay. So let's start with this. So I'm going to explain something about advanced cameras. So basically, the need for such an advanced camera is relatively simple. So our customers or the end customers, often require either smaller form factor, higher resolution or accuracy, or higher throughput, or all three of them. And that is actually they have the need for such an advanced camera, of what we call an advanced camera. So here I present the 4 pillars that we use as a definition for these cameras, starting with high data rates. So I saw in the presentation from Teledyne FLIR that at the top level was somewhere at 7 gigabytes per second. So that's actually roughly where we start. So we are in the range here at 50 to 400 or even higher gigabits per second. So that's massive data. And I'm going to try to explain a bit how we are solving that a bit later in this presentation. Then to enable that, you need, you often need custom image sensors. So you can't produce such a camera with off-the-shelf image sensors. So you need to do some customization or completely new designs. So that's also something that we've done already quite often in the past. Then, as I explained, there's the form factor. Our customers need it to be smaller or even the same form factor, but higher performance. So that brings in some challenges in terms of thermal, mechanical constraints. I'm going to show you some examples of some specific issue that we have is operating cameras in vacuum, which is, I don't know if anyone needs it, but it's rather cool. And then there's the need for embedded processing. So at some point you need to process the data, and depending a bit on the application, that can be inside the camera or in a kind of a big server rack or whatever. So just to show you some example, I'm not going to stop here for a long time, but these are some examples of advanced cameras. So this one doesn't have a high data throughput, but the form factor is very important. So it's very small. We have it at our booth, then you can really see it. But it was a retrofit. So this product was existing, but the performance was not enough. So they needed to increase that in the same form factor. So it's a form-fit function compatible device with higher performance, including the processing and the optics included in the product. Totally different application, super high data rate, so up to 400 gigabits per second, so really significant. In need of a custom silicon device, in ultra-high vacuum, so it's not the normal vacuum that you know from your vacuum cleaner. It's much lower. This is a more space-like vacuum. And it has active cooling to get the temperatures down to get the right noise levels. Another one, so they don't always look like cameras like you see here at the other stands. So this again is a high data rate, 160 gigabits per second, custom silicon. It actually a stacked image device here, ultra vacuum as well, and water cooling. Okay, so if you need a custom image sensor, so we often need it. You often start with the pixel design, so that really defines the performance of such a device. And then you go from the pixel until the interfaces, or the pads around or on the edges of the die. And that is actually where integration in a camera is, that's where the challenges actually arise. So I'm going to explain something about the sensor interface, the bonding technologies that we see and that we have, having the layout of those bond pads, and also showing something about custom placement tools, because you need to also put it in a camera. So if you see this list of all kinds of specs that you need to think of, they're not independent, so they're all intertwined and all dependent of each other. So if you make a choice in one, you need to probably tweak another one as well. So for instance, for the interface, you can go for a standard MIPI interface, Aurora, some proprietary protocol, GSD204B. There are a lot of those, but it always is the question, what are we going to do? How do we get that massive amount of data out of the sensor? You can either do that with many lower speed interfaces, so lower than 1 gigabit per second. You need 100 of them to get 100 gigabits. Or you go for less, higher speed data lanes. But yeah, you need to make that, put it on the board, etc. So that comes a bit later as well. Then that depends also on the distance between the transmitter and the receiver. If that's very long, maybe you shouldn't go too fast. But yeah, you don't want 100 traces going for a meter. And all that, you need to think about impedance matching of the whole signal, starting at the sensor to the FPGA. So there's a lot of things to think about there. So these are some of these challenges here. Then regarding the bonding technology, so eventually you made a decision, okay, I'm going for this data interface, this speed, and then you need to think about where to place the bond pads. Are we going to do wire bonding? Are we going to do bump bonding? Stacking of dies to make everything possible? Those are all things to think about. So I have here some examples. So here on the bottom right, you see some wire bonding, and well, on the right side actually. Well, yeah, you need to also think about the quality. If you have such a high amount of connections and high-speed connections, yeah, you need hundreds or even thousands of such connections per image die. So it's not that easy. And then, okay, you have defined your device. Then you need to place it on some kind of circuitry, some printed circuit board, some electronics, so to connect it. And then, yeah, you need to think about the fan out, getting the data out of the sensor onto the most probably an FPGA or a processing. You have, well, a certain amount of space. An imager can't be too big. And then you have a certain bond pad pitch to think about. Creating multiple rows, or either go for bump or ball bonding to have, well, a 2D way to connect it. These are all things to think about when developing such a advanced camera system. And then I've shown you also something about a custom placement tool on how to accurately align such a device perfectly on top of the, well, inside the camera enclosure, and being able to interconnect it, because yeah, you have a small pitch of a couple of hundreds of microns between the pads. It needs to be aligned. Yeah, it's quite a challenge. And I think the key here is to have the knowledge and the technologies and the processes all together. And that's actually what I'm trying to promote here as well. We are doing all of this. So we are thinking about the bond pad strategies, about defining such a device, about building a camera. We're producing cameras, and this advanced packaging as well. We're doing all of this. So I introduced high data rates already. So we now have an image sensor with a high data rate. We got it inside the camera somewhere in a processor or an FPGA, but now we need to get the data out. And then you need to think about the camera interface protocol. You need to think about frame grabbers and actually also the compute platform. How can you process that massive amount of data? So I depicted here some topologies. They're rather simple. So what you can do is either connect one camera to a frame grabber and then connect it to some compute platform. It's depicted here on the left. If you have such a high data bandwidth, like 200 or 400 gigabit per second, you might need one camera and multiple frame grabbers. And one other idea is, can't we get rid of those frame grabbers? Because, they don't actually do anything. They're just a way to convert the data that's coming from a camera interface to your PC. So can't we get rid of that? So that's why in the table I listed 3 options that you could use to deal with. The example here is 100 gigabit per second. So what you could do is use 8 lanes of co-express, which is a very widely adopted interface standard. But then you need 8 lanes of that to get it. An alternative is camera link high speed. The standard version of that runs at 10 gigabit per second, so you need 10 of those. Okay, you can do that. What we're actually doing also for our own high-speed line scan camera, we upgraded the speed of the interface to 25 gigabit per second per lane. And then you only need 4. And it's actually the same physical standard as 100 gigabit Ethernet is using. And then you can use one single multi-fiber cable that you can buy everywhere. So it gets rather simple to at least interconnect it. And then the last thing is, you can also go for 100 gigabit Ethernet. Then you need to do a bit more in the camera to do that. But at least you could get rid of your frame grabbers, which is a benefit, of course, because you need less components. One way to do that is eventually, with such high data rates, to use RDMA, so remote direct memory access. And you can actually distribute that data over multiple compute systems. And then you can, because one computer might not be able to handle the speed of one camera. So in this way, you can distribute it. It's something that's coming, but it takes a while. The thermal and mechanical constraints. I show here an example of a heat exchanger that we developed some years ago. You always have the question, what kind of cooling medium are we going to use? Are we going for air cooling, water cooling? Yes, some benefits, yes. And so some pros and some cons. This one, so the one on the background, is used for active cooling to further cool down the system. And then, that's the special thing we have. So cameras inside vacuum. So I'm going to show you something. So here I show some examples. On the top right, you see some thermal simulations that we do, because you need to get rid of the heat in the image sensor, the FPGA, the power supplies, and all the other electronics inside such a camera. So that's why we do extensive thermal simulations. Also, you see a warped imager carrier actually there. It's exaggerated, that's how you look at it. But if you have mismatches in thermal expansion, you need to think about that to build such a camera. Then you have the question, are we going for water cooling or air cooling? It all depends. So water cooling is slightly smaller, so a small form factor is helped with water cooling, but you need the water, so it's slightly more difficult to integrate that one. then, well, we are familiar with doing thermoelectric coolers to actively cool down the image sensor to get sufficiently low noise. And then for the vacuum, so yeah, you can see there on the picture, so a vacuum setup to measure such a camera, whether it's vacuum tight. You need to do that with helium leak testing. And you need to also be careful with virtual leaks. And you potentially need to bake out some components to get rid of the outgassing of such components. You are restricted actually in some components inside the vacuum. So yeah, that's also one of the expertise that we got in the past years there. And of course, all this within a small or similar as the previous generation form factor. It's a short time to explain everything. So then embedded processing. So back in 2007, when I started actually at Prodrive Technologies, my colleagues were finalizing the first camera with embedded processing. So as I said, we're not a young company. We are there for some time, but we had a camera for traffic observation running. Well, we were providing all the drivers, the libraries that had JPEG 2000 compression inside. And our customer was actually building its own code on top of that camera. So they were defining the algorithms running additionally on top of the camera. So inside the camera. So we really had to cooperate with them. And that's something that we see more often. So it's always the question, do you want the raw data output at full resolution, full bit depth? That's something that I explained. Then you can have that high data rate. Most often we at least do some artifact correction. So fixing the defect pixels or the defects, doing flat fielding, offset, gain correction. But yeah, we offer as well some embedded processing dictated actually by the end user. So it could be that they are really coding on top of your platform, or that they are providing example code like a MATLAB or a Python script, and that we are integrating that in the camera. So I'm just within the time. I have some time for some short questions. Thanks.
Impressive camera technology, pushing the boundaries.
It's something else than the others are showing here, I think, yeah.
No questions from the audience? There are no questions in the chat room, but I would like to ask you one. So what industries, what applications do you see them for?
Yeah, so we are mainly, for these really high-tech cameras, we are looking at life sciences, semiconductor, and some other industrial markets. It can be a lot.
Thank you. No question? Well, thanks to all the speakers, giving us a huge range of innovation in camera technology, from low cost to high-end, from easy to use, from very specialized, customized camera technology. Give them a hand. Thank you. And all of you, have a good vision show. Bye-bye.